Thank you for the introduction. My name is Tobias Mascetta, and together with Gerald Wirschling and the Tome Chair of Artificial Intelligence, Robotics and Real-Time Systems in the CPS group, for some years now developing CommonRoad. And for the last challenge, for the last Autoware challenge, we developed an CommonRoad to Autoware bridge for effortless rapid prototyping of motion planning algorithms using CommonRoad. So first, let me show you a short video where here we are, a short video of some test drives we made. That's at our university in Munich in public traffic, and as you can see here, was last summer where we first had our test drive with some, I'd say, decent amount of traffic and some unforeseen like pedestrian movements. And here it was. And most people who do motion planning actually want to test their motion planners in real life, but it gets very hard to do so because you need an entire software stack. And the research community usually depends on Python, but software stacks are usually in C++. So we thought it would be good to give something to the community where you can use your motion planner in CommonRoad with Python and just integrate that into the CommonRoad, into the Autoware software stack. And that's what I'm presenting today. Okay, a little bit for the content. I will give you first a little talk about, okay, what is CommonRoad to Autoware, how to couple it, and some recently featured papers which prove that it is actually used by researchers and that it actually can help you get your papers published. And then a short review of what we're currently developing. So we're still upgrading our research and our CR2 Autoware for you to use. And then there is a tutorial on how to use it and what to do with it, which has two sub-tutorials. One is how to use the interface, and the second one is a bit of a broader or more abstract topic on how to integrate your own stuff into Autoware, which is just our experiences. And we thought that might be helpful too. Okay, the CommonRoad benchmark suite, as you can see here, comprises of now more than 50,000 scenarios. This slide is a little bit older, but we have some XML file which gives you all you need to know about the scenario, including lanelet, structure, traffic participants, static, dynamic obstacles, and their predicted behavior, as well as regulatory elements. And you can see them here. We have a lot of simulated scenarios from our scenario factory, but we also have a lot of real-world dataset and real-world dataset converters, for example, to the entirety of the highly XD dataset that you may know from your own papers and our own dataset from Munich. So there's a very broad database you can rely on, and we have a lot of active users, mostly from the research community, and everything is installable via PyPy, which might be useful to you as a researcher. Okay, we also have surrounding CommonRoad, the CommonRoad software environment, let's say it like this, which has several different substructures. Most interesting for you may be the motion planner substructure, where you can use different parts of the motion planning pipeline which you don't want to develop yourself. For example, you need a route planner, you need a reference path planner for Fresnel-based stuff, or you need a velocity profile you can rely on. And those we offer too. We also offer a lot of tools regarding vehicle models, dynamic models, kinematic models, and analyzing tools like criticality measures. And we also have a lot of sim-to-real and real-to-sim to software components, for example, the interface to Color, the interface to Autoware, and interfaces to other software parts where you can use CommonRoad for your own research. Okay, why did we choose to couple CommonRoad with Autoware? It's fairly easy. CommonRoad is, we would say, easy to use. It's good for benchmarking. It's easy to reproduce, and you can use it for rapid prototyping in research. But we don't have a perception module. We currently don't have a control module. We don't have an autonomous software stack. All of that is offered by Autoware. But as you know, Autoware is C++. It's also a rather complex software stack. So we thought, well, they kind of are complementary to each other. And that's why we aim to fuse them. Okay. That was our mission statement here: bridge these two open source platforms and use them together. And that's what we did. I will go through that a little bit faster, you can read all of that up in our paper, which we published last IB. Basically, what we did, we took out the entirety of the planning module and put CommonRoad into it. We have interfaces to all the other software stacks, including the API from Autoware. And inside that, you can use, inside the blue box, which is planning, you can use CommonRoad. That's the high-level message. Okay. For using our software architecture, we thought it would be easy to make you to develop some sort of easy architecture. So we have two main paradigms, which are handlers and interfaces. Interfaces are the simplest version of what you know as a software interface, from which you can inherit or concretize, as you want to say it, your own planner. For example, if you say, hey, I want to have a trajectory planner, then you can inherit from the trajectory planner interface and code your own example planner in there. And as if you implement the abstract methods correctly, it should work inside the CommonRoad to Autoware node. We also have handler classes that ones you most likely won't have to touch, because these are handling the scenario conversions, the data set generation, the API handler. You also get some form of data out of it if you want, which does not rely on Autoware to be converted to CommonRoad, but has a separate script. So you can, which we already did, drive somewhere and convert what you've seen in the environment model as a CommonRoad scenario, which might be nice for your papers. So you have a little extra GIF or something you can show the reviewers. Okay, here are some screenshots from the simulation. The current version of CommonRoad to Autoware runs on the Autoware release from last year, but we're updating in the newer version to the newest Autoware version in roughly 2 to 3 months. And you can see here a planning simulation. Here's a Frenet-based planner, which drives, that is a street at Campus Garching from TU Munich. And here you can see the real test drive at the same street. You can see my colleague Gerald here, that's my own car in front. And we are driving inside the university streets. And yeah, that was one of the first test drives where we actually had CommonRoad on a real street. Okay. Our mission statement was to do this, to make this for researchers. And so it would be good if people actually use it to publish it. And that's what we did. So as you can see, these are a few examples from our group, because of course our group knows CommonRoad. So it's fairly easy to them to use them. And most proud of, I think we are from a recently published article in the Proceedings of IEEE. That's a rather high-tier, top-tier journal, where a few colleagues of ours that are more on the theoretical side of things and never have worked with Edgar or anything with Autoware published or put their work onto Edgar and did real-world experiments, and that was one of the boosts which got them through the review process of a top-tier journal. And what we did there, or what the colleagues did there, was to use formally correct traffic rules and provably correct motion planning, so more from the software verification theoretical department of our chair. Yeah, then there's a journal article in review from a colleague of ours, which did a bit of rule-compliant trajectory pairing, which is in the, let's say, middle between theory and practice. And then that last one is for myself. And that's what I will be presenting tomorrow, is a new CommonRoad tool, which is global planning. As you can see here, through the entirety of our chair, which ranges from very theoretical mathematicians to practical guys like me, we were able to use that in our publications. And we hope that you can use that too. Okay, so in summary, our CommonRoad to Autoware interface simplifies rapid prototyping. It takes care of the heavy lifting of integrating your stuff into a real-world capable software stack, and researchers can focus their valuable time on improving their own algorithms and their own work. And we actually achieved a combination of two large autonomous driving ecosystems, where you can first benchmark your code on just CommonRoad scenarios on your own laptop, and then if you so desire, put them into your own vehicle, which is run by a CommonRoad Autoware interface. And it's all open source and maintained, and actually even developed further, and you can use it. Okay, here are some links, and that concludes the first part, longer part of my talks. As I said, here are the papers. There's a GitHub repository and our CommonRoad website where you can find all the information. Okay, presentation is over. And that's a little slide that I wanted to share. That's actually 3 slides, which is the preview of the next CommonRoad to Autoware major release. And I present this because of 2 reasons. Number one, it's interesting for you because it focuses on how to make behavior planning or the behavior parts more modular for you. So we introduced some building blocks, which I'll explain in a moment. But the second part, why it might be interesting for you, is because most of that or all of that was done by my student Sven. So this is actually a master thesis, and it worked on the real vehicle. So it also shows that CommonRoad to Autoware also enables your student, or at least good students, to work with real vehicles in their own master thesis, which is quite nice if you have some teaching opportunities or duties, or you have good students that you want to actually give something for their master thesis. Okay, what is up in the new release? We focused on, as I said, behavior planning and how to make that more modular. We have two concepts here, a high-level state machine and a behavior level behavior tree. So the high-level state machine is what you expect of a state machine. It's just some building blocks which enables you to easier tingle with the internals of how Autoware or the CommonRoad to Autoware interface handles the different Autoware states, if you so desire. For example, this slowdown here, which I will show you in the next slide, is actually a placeholder for something like a safety layer. So you could put new blocks here and get some state transition logic for you to actually like further develop or further build upon the CommonRoad to Autoware interface, if you so desire. And the other one are behavior trees, which some of you may know from computer games, which is usually used in modern computer games, at least, to have some sort of NPC battle logic or something like that. And you can also use that in autonomous driving behavior if you want. Okay, first, the overall planning logic. As I said, for example, here we have these three building blocks are what the CommonRoad Autoware node does, but in a more abstract way. And now we have blocks, for example, a safety slowdown, which you can just put in there more easily and more abstractly. So you don't have to go into the deepest of the CommonRoad node to Autoware node, but you can go one building block more in the abstract, which is usually nice for researchers. The more interesting stuff for you might be the behavior trees. You can see here the behavioral logic for a green light passing. I won't go into the details how behavior tree works. You can just Google it. It's a fairly well-known concept, but we were able to put them to several use cases. The most promising one, of course, is traffic lights, but we also have a behavior tree for lateral obstacle or for lateral obstacle velocity adjustment, which you can see here. For example, if a vehicle drives close, we slow down, or if there's a parking vehicle, we also slow down. And we also have lane keeping and no lane keeping now, which before that, or in the current release, are stuff that your planner actually has to do itself. But now we also offer building blocks. If you want to build that behavior outside your local planner, you can do that here. And I have one just little video for you for how that green light may, or how that traffic light may work. As you see here, here is a traffic light, so we put it there as well. So you can see traffic light. Here it's a Frenet-based CommonRoad reactive planner. It's the CommonRoad velocity planner for the velocity behavior, but abstracted in a behavior tree. And now we see here, there's also a red light. Now it switches to green. I have to manually say, okay, but that's a safety feature for development. And now we're driving again. So yeah, we hope that this is also something you would enjoy as a research tool, and also maybe enjoy working with your students on. Yeah, that were the real world experiments I just showed you. And now we're coming to the basic Autoware tutorial. Are there questions to this point here? No. Okay. Then the tutorial one is actually how to use CommonRoad to Autoware. And the very basic overarching software concept is your planner should work inside our CommonRoad to Autoware node as it would work inside a CommonRoad-based Python script. So you don't need additional knowledge. That's basically the selling point we want to make. And therefore, we convert everything into a CommonRoad scenario. You are able to use the entirety of the CommonRoad toolboxes as you desire. We have a serialized control flow, and we have dedicated output interfaces to the Autoware stack. Okay, how to inherit your planner? How to include your planner into the software framework. I already talked a little bit about that. I want to emphasize it. look into the code. There is in the interfaces you can find for route planning, for different behavior planners, and for local planners, which most of you may be interested in. Find interfaces you can inherit from, and the abstract methods just tell you what you have to implement. And you can also look at some of the planners we already implemented on how to do that. I will show you a demonstration of the planning sim in a moment. First, however, I want to introduce a little bit the core technology we're using, and that core technology was not only developed by CPS, it is, as the Autoware project in general, developed by 3 chairs mostly, Professor Johannes Witt's chair, ADS, Professor Liekamp's chair of automotive engineering, and us, CPS. And the core technologies and how they were integrated in our software was mainly done by FTM, Gem Cagliaresi here. We use a Docker Compose architecture. We use a GitLab CI to build those Dockers and use VS Code with a container add-on so we can actually go inside the Dockers, code with them, and then just use GitLab to push and pull and rebuild. And the basic steps are you attach to a running container, you code inside it, you build your package, you source it, and if you don't want to push them in your repository, you have to Docker stop or Control-C, so kill the container and go use Compose thereon. Okay, so before we go forward, I want to show you a little bit how that works. So as you can see here, we have 2 Docker Compose commands. One of them is just the Argus. Okay, you can't see them really, but and one of them is the rest of the software stack. And as you can see here, it takes a little bit because my computer is slow, but at some point Argus will start. Yes, it started. There we are. You can see here, this is, if we scroll out a little bit, this is actually TU Munich. This is Campus Garching. And let me just deactivate the point cloud, then it gets faster. Yeah, here we are. So for example, this is where Edgar is usually sitting here. And you can say, okay, I don't know, we start somewhere here and plan 21, 22. Yeah, there we are. And plan to somewhere here. And this is the CommonRoad route planner, which planned the route, and the CommonRoad velocity planner, which planned the velocity. And as you may have noticed, we didn't press auto yet, as you may have noticed. It took the local planner a moment to initialize, which is the first time that you run the software. We use Numba to precompile most of the Python local planner to have a better performance on the car, which is something we can recommend to you to use as well if you want to work on the real car. And now we can just press auto and hope that, yeah, perhaps if the screen button is not there, but you can see that it drives. So this is the CommonRoad reactive planner, which is a Quenet-based motion planner. The optimization planner is a the velocity planner is an optimization-based planner. And yeah, as you can see here, we're braking rather hard. Yeah, and here we are. Okay. And then the velocity, the limit stop, we have to update that there's actually a 0 here. But that's how about the planning sim in its most basic form works. And we can highly recommend that workflow, as I said, with a Docker Compose structure here, which also separates Argus and the rest of the stack. And yeah, that's something you can also look forward to is the Wiesen release, which is done by our 3 chairs, where you can see the entirety of the Wiesen software stack that we were driving, where we actually used the entirety of Autoware with some adjustments on our CommonRoad. But you can see you can use that to build CommonRoad inside as we expand our GitHub repository. What we see here is the reactive planner interface. That's the planner I just showed. I would, if you want to use your own planner, look for the reactive planner interface in the code and just look where this is and how to be implemented it, and then you can very easily do that as well. The estimated effort is depending on rather depending on how well you know CommonRoad. Let's say if you know CommonRoad, which our theoretical guys did to a certain extent, you need 1 to 2 days per planner. If you don't know CommonRoad, you have to acquaint yourself with CommonRoad that is on top of that. But in our chair internal user test case for the proceedings pad, it took 1 to 2 days per motion planner to integrate it to. Okay. Then the question is, okay, how do I use CommonRoad? And I debated to myself whether or not I would show you, I would stand here and code for half an hour to you, but I don't think that makes too much sense. I rather say, okay, look to the CommonRoad website, because every tool we have has a dedicated documentation. And the most important thing you have to understand and you have to look into is the CommonRoad scenario, because that's also what we use on the car. And you can't read it here really, but this is the line where we import the scenario and the planning problem. And from there, you can do whatever you want. And I have here a little bit of, this is our CommonRoad website here, for example. We have some video here. And let's say you want to do motion planning, and then you click on the CommonRoad velocity profile planner because you want a velocity profile for your local planner. Then you end up on this page, which already gives you a little bit of basic usage information. But then if you want to go further, you can click on documentation, which brings you here, which is a fully documented site where you have some example usages for how to use different methods, different classes. You have a minimal usage, you have a long example. So you have quite a lot of things you can read through if you ever want to use such a tool. And that exists for every CommonRoad tool. So it's should be fairly easy for you to integrate your plan into CommonRoad, and then it should be fairly easy to integrate it into Autoware using CommonRoad. Okay, that is mostly the first tutorial. I just want to again emphasize that we have a whole scenario benchmark where you can actually test your scenario, your motion planners on our website. And we also have a lot of dataset converters for real-world datasets, which are now called the level X datasets, which are highly exit around the interaction. There are a lot of datasets. So if you ever want to say, well, I'm not sure if my planner works on real scenarios before I put it on the card, you can use our converters and just download or contact these people to give you the dataset and convert it with our open source tool to CommonRoad. Okay, final slide for that one is the reminder of, okay, we have quite a lot of stuff you can use. That's the basic overarching theme of this slide. I won't go into detail of it, but I can highly recommend looking, for example, into the criticality measures and a lot of the motion planning utilities that we have. Okay, now to tutorial 2. But first, do you have questions for tutorial 1? No. Great. So this one is a little bit more of like our. Okay, we have questions.
Sorry, maybe Tobias, I missed. Did you also say what kind of computer setup I need to get this started?
Well,
do I need like super duper Alienware?
No.
Yeah, can you tell us?
Yes. So it runs on this machine, which it's a good laptop. It does not necessarily need a CPU, a GPU. I'm currently running it actually on my CPU, which is a rather powerful one for laptops because my GPU isn't working, but it gets faster with the GPU, of course. So I'd say higher end laptop or decent enough desktop suffices. So we're running this on our lab PCs. We're running this on our student PCs. I'm running it on my laptop. A colleague of ours ran it on laptops which are less powerful than that. So I'd say a modern day research grade laptop should do the trick for you. Thanks.
Just a quick question about like, has anybody tried within your research group using like reinforcement learning with this?
We have a rather theoretical part of research group which is currently looking into it.
Okay.
But the methodologies are not at a point where they are capable to do real world stuff. So the answer is no, with the exception that on the proceedings paper, Roland, our colleagues also, he works on mostly theoretical reinforcement learning, but also has some sort of set-based prediction in it, and the set-based prediction part integrated. So I'd say if that's your knowledge, then you should be able to use it. Reinforcement learning depends on how long the guys from theory needs to put it closer to practice, but I'd say it takes a year for them roughly, but if they're bringing it to practice, they use this. Okay, further questions? No. Okay, then the second tutorial is a little bit more of like a detached version of what I told you now, which is a general version of how to couple your software with Autoware. And this is more of our opinion. So Gerald and I thought a lot about it. People from ABS, from FDM thought a lot about it. Okay, what's the best trick to do it? And our audience is a research audience. And therefore, we said, okay, there are mainly two ways to put your package, your ROS, however, package into Autoware, which is a built-in package and an external package. Then do not differ too much. Both of them need a dedicated package structure and an integration into the existing launch structure. But the main difference is where your package is, who has access to it, and how easy it is to deploy and to prototype with. And the basic two versions we say is, okay, the built-in package, easier to do rapid prototyping, easier to code with, easier to get into it, but you have to do constant adjustments. So you just put it into a folder, you just git clone Autoware, you put it in there, you kind of make your local adjustments to the Autoware launch file, and then you work with it. This is nice for rapid prototyping, but of course, if Autoware changes, you have to adapt to those changes. An easier version is, or a long-term easier version is the external package. You have everything in an external repository and adjust the Autoware launch structure on a higher level. But of course, for that, you have to know something about the Autoware launch structure. And I just give you a very brief rundown of how to do an external package. This external package is the operated driving notifier developed by Team Planning, which is ADS and myself, and our colleague from FTM who does the system part. And basically what we have here is a very simple C++ node which contacts the tail-operated driver or signals the tail-operated driver that we're standing somewhere although we want to drive. And as you can see here, for a package, there are two main parts, which is the package XML and the launch directory, which calls a launch XML. And in the package XML, well, quality is not too great. You just define, okay, what does dependencies of your package, what's the name of the package? And in the launch XML, you tell it, okay, what's the package name you want to launch, or you depend on what is the executable you want to launch and what's the name of it. And these files, there's a lot of examples in the Autoware structure you can use to build this package. So we highly recommend use a structure like this. And then Git repository for us, it's actually AV software, just an external GitLab group in our case. And then we have a repository here for each external package. And that worked quite well for us. Plus side on that is you have user management on top of it because you have GitLab. So you can very easily give access rights to whatever students and with the well-known Git user management system. And then the second question is, as I said, okay, how do I get this into the overarching Autoware launch structure? So Autoware has a per component launch, which are some, as I call them, dummy packages, for example, for the system component here, which is just a package which launches other packages, or node which launches other nodes, to be precise. So what you want to do is, okay, you will find that node for your, or that package for your, where your external creation fits best in. For us, that was the system package. You find the T4 system launch in our case and find that package XML. And in there, I will show the slide or share the slides later, but in there you just have to say, okay, we have another dependency, which is our own package. We want to launch it with certain arguments. And then if you have some sort of CI building tool, you also want a .repos file, which just tells the CI, okay, where do I actually get the code from? If you want to have, for example, we have GitLab CI, then it says, okay, here, that's our notifier, and we want the develop branch to check out and build automatically. So it's fairly easy once you know it, but getting to the point of actually knowing it takes a bit of effort, and that's why we have these two slides here. Okay, and the last one, which is a proposed development workflow that AWS and CPS and FTM mainly came up with, which is, okay, now I have an external and have an idea how to integrate my external package, but the code-wise, how do I actually get input and output from Autoware? And what we propose you to do is do it in a more academic way, which is, okay, do a minimal viable product pseudocode. You just say, I have input X, Y, Z, wherever they may come from, and you write your pseudocode logic. Then explicitly say, okay, what are my outputs, what are our inputs, what do I actually expect to get from Autoware? And then third, and that's the main part, is search the Autoware inputs in a recursive manner down to the primitive data type building blocks. What do I mean with that? Like, let's say you have a message here, can't read it unfortunately, but that's a trajectory message. Trajectory message, okay, contains trajectory points. What's the trajectory points? Well, it composes of a pose and a, let's say, longitudinal acceleration. The longitudinal acceleration is a float. Perfect. Your first primitive data type. But what suppose? And then you go down that chain until you end up with only primitive data types that you understand, because that you can access in every, or most of them you can access in every programming language, especially Python. And how to do that is we propose this like simple table. You have your topic name. You want to know, okay, do I get this like in a frequency, or is there some sort of trigger and I have a fixed occurrence? What kind of message type do I get? And this is the recursive one, as I said. And where do I find, what's the definition of this message type? This field is the most important one because it helps you to grasp and understand actually what the data types are that you have on a, as I said, primitive level. So float, string, etc. And here I would really recommend you to copy every link of everything down recursively into there. It makes development afterwards so much easier. And then you can have possible value types, which might be interesting for you if you have some states dependent stuff, and then the desired values. And that in and of itself gives you a very easy protocol, or let's say cooking recipe kind of way to actually build your own stuff into Autoware. And there are some useful commands here. You may know them from ROS. I can only highly recommend to Google these ROS commands, Google the commands that you have, make a list of what they do. Also, most of them have a -v for verbosity, which also gives you a lot of interesting info. So this one you may need to actually find out, okay, what message type do I get initially, and from there, Googling start. But here's the link of where Autoware puts their messages. It's actually well organized repository. You just have to know where it is. Okay, and with that, I'm at the end, on behalf of myself and Gerald Wishing, special thanks to the entire Edgar team at CPS and ABS, and of course to the Autoware Foundation for giving us this opportunity to present our work.